Okay, in today's session we are going to solve the previous year questions of transformers. In last two sessions okay. Let's start the session. Okay, the given question is about a 230 by 2300 volt transformer takes no load current. Concept is the concept is about core loss calculation. Core loss calculation. Okay, from the given data, what and all we observed is it is a telling about no load current. So the transformer is at no load. That means the current taken will be very less. That means it is about 5 amps and power factor is 0.25. So since the transformer is at no load, whatever the power drawn from the source, completely to meet the losses of the transformer. If you see at no load condition, what type of losses will come? Okay, what are the different losses will come? No load copper losses will be there. No load copper losses and constant losses. Constant losses are iron losses. Constant losses are iron losses will be there. Okay. So since the no load current is very small, this no load current will be negligible. No load copper losses will be negligible. Okay. So whatever the power drawn from the source completely is going to meet the constant losses. That means to meet the iron losses. So the power consumption or power drawn from the source, we can write it as no load power consumption or no load power drawn from the source is written as V into I naught into cos pi naught. Okay. So now no load current is clear, the given I naught, but which V we have to take? Since they're telling no load current, no load means the secondary is not connected to any load. So primary is excited. So we need to consider the primary voltage here for calculation. So 230 into I naught is 5 amps and power factor is 0.25. Okay. After doing calculation, how much it will come? Let's do the calculation. So it's near about 287.5 watts. Okay, the no load power consumption is completely to meet the losses of the transformer. The losses are iron losses. Okay, is it clear? Okay, we'll move on to the next question. Okay, the question is about in a three-phase delta transformer, one of the phases has input up. The transformer will then. Okay, if you see the question carefully, what they are telling, the given transformer is a three-phase delta transformer. Okay, the given transformer is a delta transformer. It is a three-phase delta transformer. Okay, what they are telling, one of the phases has input up. That means one phase got faulty. And that may be removed. Okay, so one phase got faulty, that may be removed. Then the delta is going to be open delta or open delta or what you can say VV type connection. Okay, if one phase is faulty, means the delta is going to become open delta connection or VV type. This is most important question. Many times it is repeated in so many competitive exams, even GATE and IAS also it is repeated. So we need to clear about the concept here. No need to get any confusion. What they are telling, they given a 3-phase delta transformer. In that one phase got input up, means one phase may be faulty and they removed. So if you remove a one phase from the delta connection, so it is going to be VV. Okay, it is going to be VV type or open delta connection. So the question, let's see the concept. Which question? The question is coming from the which concept? It is a VV connection or open delta connection. Open delta connection. If it is like that, what they want to find out, the transformer will then supply. What they are asking, KVA transfer. For suppose if it is a delta transformer, how much power is going to be transferred? Since one phase is out, it became VV type or open delta transformer. How much power in open delta transformer is going to be? They are asking about the comparison. Okay, they are asking about the comparison. Let's see how to calculate the power transfer by a transformer with the help of the phasor diagram. Okay, let's see. This is V1. Let's take it as IL, or you can take it as VL IL. Let's take this is the phase current I1. In delta connection, we know line current equal to √3 into phase current, √3 into I1. Okay, clear? Here also what will come? This is the line voltage. Now this will be the primary current will going to be I1 only here. Okay, so first we will calculate the power transfer KVA capacity of delta KVA rating. We can calculate how much it will come. Normally what is the formula? √3 VL IL. KVA calculation of 3-phase transformer is √3 VL IL. Okay, so from the first diagram, let's take it as a figure 1, let's take it as a figure 2. From first diagram we can see √3 into V. What is the VL? VL is VL only. IL you can write it as √3 into I1. So √3 into √3, it is going to be 3 VL into I1. So the delta KVA rating is going to be 3 VL I1. Now we will calculate the KVA capacity or KVA rating of the open delta connection or VV connection. If you see VV connection KVA rating, you can write it as √3 into VL IL. What is VL? VL is same. What is IL? Here IL is I1. Okay, clear? Let's take this one as equation 1. Let's take it as equation 1. This one as equation 2. Okay, so if you do equation 1 by 2, if you do, what will come? √3 VL I1 divided by 3 VL I1. After cancellation of this, it will become 1 by √3. What is equation 1? VV KVA rating equal to, or VV KVA rating divided by delta KVA rating equal to 1 by √3. It is about 0.577. Okay, so therefore the VV KVA rating or the power transforming capacity of the VV type connection is going to be 0.577 of delta delta kVA rating. Okay, delta delta kVA rating. This is very important question, repeated in many times in the competitive exams. Let's see the options. What are the suitable options for this? Okay, they are given in the percentage. If you calculate the percentage into 100, if you do, the options are in percentage, so if you multiply with 100, you will get it as 57.7% of rated capacity. Okay, rated capacity of delta delta. Okay, so in our theory classes, you might have studied about the open circuit test. In from open circuit test, what and all we are going to get? We can find out the constant losses, shunt elements like R naught and X naught, and we can separate the iron losses into hysteresis loss and eddy current losses. We can just check the given options. Copper losses, no. Copper losses need to be calculated at rated current. Okay, we need to calculate at the rated current or full load current. Since we are doing at no load test, copper losses we can't calculate accurately. So this option is not correct. Next, total equivalent resistance. So for calculating equivalent resistance also, we need calculation of the losses. That means copper loss. We need to conduct the test at full load condition only. Okay, full load only you have to conduct the test. This also not correct. Third option is turns ratio. Okay, turns ratio we will see. We will go to first D and come to the C. Okay, what is the last option? A total equivalent leakage reactance. That also we can't find out. Leakage reactance total you can't find out. So it depends on the secondary current also. Okay, so this also you can't find out. So we'll see whether you can calculate the turns ratio from this open circuit test or not. So we already know that at no load, the current is very small. That means I naught is very low. So the voltage drop also very less. Voltage drop also is very less. So then E1 is nearly equal to the E2. Okay, from this what you can find out is E1 by E2 you can calculate. Okay, E1 by E2 you can calculate. E1 you can get from the applied voltage, that is rated voltage. Okay, applied voltage or rated voltage. Since the current is very less, the voltage drop is going to be near about 0. So E1 is near about E2. So okay, from this you can calculate the ratio of E1 by E2. So what we can say is the turns ratio you can calculate from open circuit test. This is the suitable option for the given question. Okay, we'll move on to the next question. We'll read out the question first. The question is given as a transformer has full load copper loss of 400 watt. The copper loss at half full load will be. So they are asking about the copper loss calculations at fraction load. Okay, first we will write down the concept on which concept it is came. Copper loss of transformer. What is the formula we know for calculation of copper losses? Okay, copper loss at any fraction of load X is given by X square into copper loss at full load. Okay, this is the formula we know. Okay, let's note down the given data. What is the given data? Full load copper losses they given. So okay, full load copper losses is given as 400 watts. What they are asking, copper loss at half full load. The fraction load of what is the fraction load is half load. That means 1 by 2. Okay, let's substitute the given data into our formula. We can get copper loss at half full load. It can be calculated as X is 1 by 2, and copper loss, full load copper loss is given as 400. Okay, that is 1 by 4 into 400, it will come around 100 watts. So our option is D. Is it clear? So these type of questions are repeated many times in the competitive exams, so you can easily answer this type of questions. Don't get confused, come from the basics and substitute the given data. You can solve the question very easily. Okay, let's see the next question. The next question is about, in short circuit test on a transformer, we generally short circuit. Okay, what is the concept of the given question is, what is the concept? They are asking about short circuit test of transformer. Short circuit test of transformer. So we might have studied already in theory that what is the importance of short circuit test, why you need to conduct. First thing is to find out the copper losses. Full load copper losses. Okay, full load copper losses. Second thing, equivalent resistance of the transformer and power factor of the transformer, etc. Okay, etc. So in order to get the full load copper losses, we need to conduct the test at rated current. Okay, we need to conduct the test at rated current. Okay, so we need to conduct the test at rated current. That means whatever the current, whatever the power you are drawing from the source is directly going to be to meet the copper losses. Okay, so the power drawn from the source during short circuit test completely to meet the copper losses only. Okay, so this is going to be the waste of energy. In order to minimize this energy, what we need to do? We need to conduct the test at HV side. Why HV side is more preferred means, HV side, if you see, the current will be small and voltage will be high. Why? Because the kVA of a transformer is constant. If voltage is high, to make the kVA as constant, current will be small. That means if you apply small rated current, that means small voltage at HV side, we can see with the diagram. Okay, if you apply small voltage at HV side, we can get rated current flow in the LV side. Okay. And the selection of meters, okay, to measure the voltage and current in the primary side will require very small meters. Why? Because we are applying only a part of rated voltage, and since it is a HV winding, current flowing in the primary side will be also less. So for measurement, the meters what we are going to use, wattmeter, voltmeter and ammeter, the rating also will be small, as well as the power energy wastage also less. If you conduct the HV test, if you short the LV and conduct the HV test towards HV winding, that means short circuit test on HV winding, you can get the all what are the main important points related to short circuit test. That means copper losses, equivalent resistance, power factor, all parameters you can calculate at very less energy consumption. Okay, this is about the short circuit test. We will see the different options given. In short circuit test, we generally short circuit. That means what they are asking, which side you are going to short. from this we can say it is low voltage side we are going to short. What is the suitable option? Option A. Okay, in shortcut test we are going to short circuit LV winding. Why? Because in LV winding, if you conduct HV winding short circuit test at HV winding, we are going to inject very small amount of voltage such that rated current flow is going to happen in the LV winding. Is it clear? Okay, we will move on to the next question. Okay, the next question is about the function of oil in a transformer is. Okay, the function of oil in a transformer is. We might have seen different parts of the transformer during construction. Okay, different parts of the transformer during the construction details of the transformer. The concept is about oil. What is the purpose of oil to meet? What is the purpose of oil to use in the transformer? Okay, purpose of oil. First thing is, let's see the simple diagram of a transformer. This is the main tank, and inside that we are keeping our windings. Okay, core and windings will be there. This will be completely filled with oil. Completely filled with the oil. These are our insulators. Okay, this is the simple diagram of a transformer. Why we need to fill the oil? First thing is, since the current is flowing in the windings, it will generate heat. Okay, whenever high currents are flowing in the transformer, it will generate heat. High currents leads to generation of heat. Okay, so whatever the heat generated need to be cooled down. Otherwise, what will happen? The power transforming capacity will get reduced. This also might have studied in your theory classes. So the rating of the transformer is directly proportional to the heat generation. Okay, if heat generation is more, that means the rating capacity rating is going to be reduced. Okay, so you need to handle the heat generation very effectively such that the efficiency of the transformer should not affect. That means power transferring capacity should not affect. For that we need one coolant medium. Okay, so whatever oil you are using here, it will act as a coolant medium. The first purpose of oil is it is going to act as a coolant medium. Whatever the heat generated, that is going to be cooled down by the oil. How it is going to cool down? If it is a high rating transformers, there will be different types of cooling methods you might have studied. Okay, oil natural, that means that oil is circulated through radiator banks. It will, okay, whenever high heat is there, it will go to the radiator banks and come cool down at radiator banks and come down to the main tank. Oil natural, air natural. Since the radiator banks are very thin in nature, so the airflow will be high. With the airflow, natural airflow, the transformer will get cooled down. Some is oil forced and air forced. Oil forced is going to be done with the help of pumps. Air forced is going to be done with the fans. These pumps and fans in general we are going to use for high rating transformer. That means 500 MVA, 300 MVA. So in power transformers, high rated transformers, we are going to use the pumps and fans for cooling down the oil. Okay, clear? First purpose of oil is coolant. Second is, this main tank is a metal. Main tank is a metal. These windings are in conductors. Okay, conductive nature. So we need to separate our core and windings from the main tank. We need one insulating medium. Okay, we need a insulating medium. So this oil will act as a insulating medium here. Okay, so the oil will act as a insulating medium also. So from this what we understood, oil will act as both coolant as well as insulation medium between core and windings of the transformer to the main tank of the transformer. So let's see the options to provide insulation and cooling. Our option will be the option A. If you see other options, it may not be suitable. Why? Because to provide protect against lightning. So no way it related. Oil is inside the tank. How it will protect from the outside lightning? No, this is not correct. To provide protection against short circuits. No, this also not correct. How it can protect from short circuits? To provide lubrication. Since we already studied in transformer, there is no moving parts at all. Where lubrication is required, where the movement of the moving parts are there, frequent, what I can say, frequent movement is there. There we need a lubrication. In transformer, there is no moving parts at all. So this also not correct. Okay, we'll move on to the next question. Okay, the next question is about the low voltage winding of 400 by 230 volts single phase 50 Hz transformer is to be connected to a 25 Hz. The supply voltage should be. The supply voltage should be. Okay, let's see what is the concept they are asking. What is the concept they are asking? It is frequency given and voltage given means concept is about calculation of voltage. How we can calculate the voltage when frequency and all given? Okay, whenever this frequency and voltages are given, we need to ensure that what type of operation is going to happening in the given transformer. So what they are telling, the 400 by 230 volt single phase 50 Hz transformer. That means the transformer is designed for 50 Hz and voltage is 400 by 230 volts. Now what they are going to do, they are telling they are going to connect to a 25 Hz source. Okay, they are going to connect to a 25 Hz source. So here frequency is changing. Okay, whenever frequency is changing, we need to ensure that Bmax, flux density, is normally directly proportional to V by F. When frequency is less, the flux density requirement will be very very high. That means in order to make the required power flow from the transformer at low frequency, we need high magnetic field intensity. Okay, field density is required. High magnetic field density is required. So to provide that, what is going to happen? It will draw more current. Magnetizing current will be very very high. Okay, sometimes it may damage the transformer also. Okay, it may damage the transformer. In order to avoid this, always we need to ensure that if frequency is less, we need to balance with the voltage. Okay, if frequency is less, we need to balance the voltage. That means always we need to maintain that V by F is equal to constant. V by F is equal to constant, so that Bmax is going to be constant, so that the required magnetizing current may not be abnormal. Okay, clear? So from the given data, if you see, what is the given data? Initially the transformer is designed for E1 equal to 400 volts, E2 equal to 230 volts, frequency is for 50 Hz. This initially they designed for this. Now they want to connect to, let's take it as F1. Now they want to connect to F2 is equal to 25 Hz. As I already explained, we need to maintain V by F as a constant, then only our transformer operation will be in normal. Otherwise it may get damaged. Okay, so let's take it as equation 1. From equation 1, what we can write? V1 by F1 equal to V2 by F2. So they are telling low voltage winding is going to be connected to a source. Okay, low voltage winding. What is the low? 230 volts. Okay, V1 is equal to 230 volts. 230 by F1 is 50 Hz. V2 we need to calculate. F2 is given as 25. 25, this is 2. That means V2 is equal to how much it will come? Okay, how much it will come? V2 is equal to 115 volts. So our option will be C. Is it clear? It is a very simple question. Only you need to understand that for for favorable operation of a transformer, V by F need to be constant. From that we can calculate the given question. Okay, let's move on to the next question. Okay, the next question is about the core flux is of a practical transformer with a resistive load is. What they are asking, the core flux of a practical transformer with a resistive load is. They are asking the relation between core flux with the under resistive load condition, how it is going to be act. How it is going to be act. Okay, we will write down the equivalent circuit of a simple equivalent circuit of the transformer. Okay, we are neglecting all small parameters. Whatever required, that parameters only we are taking into consideration. Let's take it is the applied voltage V. This is the shunt parameters XM, R equivalent, JX equivalent. They are telling resistive load. Okay, resistive load R. This is the current IR or IL. The voltage across will be the, let's take it as VL. Since it is a resistive load, it will be in phasor. Okay, so if you write the equivalent voltage, that means the voltage calculation from the equivalent circuit, what it will come? It is VL plus IL into R equivalent plus J equivalent, sorry, X equivalent. Okay, this is the, all these are in phasors. Okay, we need to remember it is a phasor sum of load voltage plus voltage drop across the R equivalent and J equivalent. So we know that core flux pi is directly proportional to the applied voltage V. Okay, applied voltage V. We need a magnitude, no? So for calculation of magnitude, what will come? VL square plus IL square. R equivalent can be calculated as a square root of R square plus X square. Okay, this is the formula. Okay, if you calculate magnitude, it is going to be like this. As we know, flux is directly proportional to voltage. We can write it as the total parameter. Okay, as load increases, when load get increases, let's take this total value as X. Okay, let's take this total value as X. When load get increases, current will get increased, then the factor X is going to be increased. Okay, we write like this: pi is directly proportional to the square root of X, where X is this total value, this total value. From this, what you can understand, if load current varies, then X will get increase. Okay, so the core flux is, how the core flux is going to increase? The increase as the square root of the load. Okay, increase as the square root of the load. Option is C. Our option is going to be C. Is it clear? Okay, we'll see the next question. In a transformer, which of the following statement is valid? Which of the following statement is valid? We'll read out the options one by one and we'll discuss. The first option is, in an open circuit test, copper losses are obtained, while in short circuit test, core losses are obtained. Okay, just read out the question, read out the options. First thing is open circuit test. In this option itself, what they are telling, open circuit test we are going to conduct at no load condition. That means I naught is very less. I naught is very less. So with this I naught, we can't calculate the full load copper losses. Okay, we can't calculate the full load copper losses. So this option is wrong. In open circuit test, current is drawn at high power factor. I think in yesterday's session we discussed about the magnetizing current. Okay, magnetizing current is far greater than the iron loss component. So from the phasor diagram we observed that, and we observed that, we'll write again the phasor diagram. This is I mu, this is IW, this is the equivalent resistance, equivalent current I naught. Okay, so the no load current is lagging near about 75 degrees. Okay, the main reason for this is because of I magnitude. That means magnetizing current will be very high. So that's why the power factor at no load condition is near about 0.2. Okay, 0.2 to 0.3. So what is the option given? In open circuit test, current is drawn at high power factor. No, it's not correct. The power factor is going to be very low. In short circuit test, current drawn is at 0 power factor. This is also not correct. 0 power factor not at all happen. Why? Because it is having both resistive component and inductive component. So this also may not be correct. Second, we'll see the last option. What is that? In an open circuit test, the current drawn is at low power factor. Yes, current drawn is at low power factor. From this phasor diagram we already discussed in yesterday's class. So the power factor at open circuit is near about 0.2 to 0.3. So our option is option D. Is it clear? Okay, this question is very simple but little tricky. Okay, confusion is there, but if you are strong at your basics, so what is open circuit test and what is short circuit test, and what and all the step by step how we are going to calculate the different parameters, then definitely you can solve the question at very easily. Okay, let's see the next question. In a transformer, 0 voltage regulation at full load is. Okay, the question is about voltage regulation. So what is the concept? Concept is about voltage regulation of transformer. Voltage regulation of transformer. This also I think we explained in the previous sessions. Just you note down the voltage regulation curve. Percentage regulation versus power factor. If you observe the voltage regulation curve, it will look like this. Okay, it will look like this. This is lagging power factor, this will be the leading power factor. The voltage regulation is going to be 0 for a leading power factor load, and it is going to be maximum. Regulation will be, this will be the maximum for lagging power factor. Okay, let's see the options. 0 voltage regulation will be possible when if the power factor is a leading power factor. Not possible, no, it's not right. Possible at unity power factor load, no. So our option will be possible at leading power factor. Okay, is it clear? 0 voltage regulation will be possible at a leading power factor. So this voltage regulation concept also very important in transformers. Okay, just we need to remember the voltage regulation curve and voltage regulation formula. From these two only we are going to get multiple questions. If you clear about these two concepts, we can solve any question related to the voltage regulation. This also repeated many times in competitive exams. So our option will be C. Let's look into the next question. The next question is about a single phase transformer has a turns ratio 1:2, okay, and is connected to a purely resistive load as shown in the figure, okay, as shown in the figure. The magnetizing current drawn is 1 ampere and the secondary current is 1 ampere. If core losses and leakage reactances are neglected, the primary current is. If core losses and leakage reactances are neglected, what is the current? Okay, what they are telling, the given one transformer equivalent circuit. Okay, is it clear? We will write the equivalent circuit of a transformer based on the given question. Okay, based on the given question. What they told, leakage reactance is neglected. Okay, we neglected leakage reactance. This is the primary side. Leakage reactance neglected, and they told about the core loss only. Okay, but the magnetizing component will be there. Okay, magnetizing component will be there in the primary circuit. This will be the R1, this will be the XM. Okay, so in the secondary side R2 will be there and it is connected to a load of resistive load. The current given as 1 ampere. Okay, what and all other data given? They given turns ratio. Turns ratio they given as N1 by N2 is equal to 1 by 2, and they given magnetizing current. Magnetizing current IM. This is the magnetizing current. IM is given as 1 ampere. Okay, so what they are asking? I1. This primary current they are asking. Okay, they are asking about the I1. Okay, in order to calculate I1, we need to shift the secondary current to primary current. How we can shift? We know that N1 by N2 is equal to I2 by I1. Sorry, I2 dash I2 by I1 dash. This is the I1 dash current. So I1 dash we can write it as I2 into N2 by N1. What is I2? I2 given as 1 amps. N2 is going to be 2 by 1, so 2 amps. Okay, so the resultant current I1 can be written as, it is square root of Im square plus I1 dash square. Okay, clear? What is the Im? Im given as 1 square will be 1, I1 square is going to be 4. It is about square root of 5. If you observe the options, the nearby option is about C. The option answer is going to be 2.24 amps. The primary current is going to be 2.24 amps. Okay, what are the things we need to focus in a given question is, if the question is related to the equivalent transformer, okay, we need to be clear about the basics. I am always telling, in order to solve a questions in a machines, we have to be very clear about the basics. That means we need to shift the secondary parameters to primary side, primary parameters to second side based on the questions, okay, based on the questions. If you know clear about how will be the secondary voltage if you convert to primary, and how about resistance, how about current, the shifting parameters from secondary to primary, primary to secondary, if you clear about those formulas or concepts, we can solve the question easily, especially this type of questions. Okay, this is also repeated many times in gate and ESC exams. GENCO, Transco also this type of questions may come. Okay, this also repeated in some of the expeditional question also. But what we need to ensure is calculations. Okay, calculations and basic formulas. If you are perfect at those things, definitely you can solve the question very easily. Is it clear? Okay, we will move on to the next question. Okay, the next question is about a power factor of a transformer on no load is poor due to. This question we already explained just now. Okay, purely due to, because again we will see the phasor diagram. Okay, the phasor diagram of voltage versus flux. This is the magnetizing current. This will be the iron losses component. Okay, this will be the our equivalent no load current I naught. Okay, this is about near about 75 degrees. So power factor is near about 0.2 to 0.3, mainly because of I mu component. Why? Because I mu is far greater than the IW. Okay, because of that only the lagging I naught is going to lagging by supplied voltage. Okay, because of this the power factor is very less. So our suitable answer is suitable option is magnetizing reactance of the transformer. Is it clear? Okay, let's move on to the next question. The question is about, during short circuit test the core losses are negligible. This is because, okay, just see the question. The concept is about short circuit test. Okay, they are asking about short circuit test. What they are asking, core losses are negligible. Okay, core losses are negligible. Let's break down the question. Okay, core losses at what core, how we can calculate the core losses? As per actual, we need to calculate accurately core losses. We need rated voltage. Then only you can calculate the accurate core losses of a transformer. Coming to that short circuit test, we already discussed the short circuit test we are conducting at HV side. Okay, short circuit test is conducting at the rate of HV side. What we are doing in short circuit test, our main mode of short circuit test is we need to conduct the test at rated current, either primary side or secondary side, but we prefer the short circuit at secondary side, that means LV side. Why we preferred, I already explained in the previous question. Okay, that means the short circuit test need to conduct at rated current to calculate the copper losses. This is HV side, this is the primary current. Okay, so if you see here, in order to generate rated current at LV side, we need to apply only part of voltage. Part of rated voltage only we are going to, rated voltage is going to apply on HV side. Full load voltage not required. Why? Because in order to balance the kV on both sides, if you apply part of the voltage is sufficient for circulation of rated current in the secondary side. So our motto is we need to calculate the copper losses at rated current. That's why LV side is shorted. When LV side is shorted, with small voltage applied on HV side is sufficient to drive the rated current in the secondary side. Okay, so from this concept, what we understand in HV in short circuit test, we are applying only part of rated voltage, not the full voltage. Okay, only part of rated voltage only we are applying. Okay, so we'll see the options. This is about the theory of the given question. We'll see what are the suitable options for our question. Voltage applied across the voltage side is the fraction of rated voltage, so it is the mutual flux. The current on the low voltage side is very small. No, it's not correct. The power factor is high. No, it's not correct. Iron becomes fully saturated. No, it is also not correct. Why? Because we are driving the transformer at low voltage only. How it will get saturated? Okay, so our suitable option is option A. So from this question, what we need to understand is, okay, clear about the losses. That means copper losses and core losses. At what condition? That means core losses completely depends on the voltage. So we need to calculate them at a rated voltage only. What about copper losses? Copper losses completely depends on the load current. So these need to be conducted to full load capacity of the transformer or rated current of the transformer. Okay, if you clear about these two terms, you can solve the question, this type of questions very easily. Is it clear? Okay, let's move on to the next question. The efficiency of a power transformer at relatively light load is quite low. This is due to what they are asking? They are asking about efficiency at light load condition. Okay, efficiency at light load conditions. That means light load is nothing but, in general, light load is nothing but no load condition. We can consider it as a no load condition. I already explained about the no load condition of a transformer. That is a open circuit test of a transformer. What is going to happen in no load condition? The current drawn will be very less. First parameter. Second parameter is whatever the power you are drawing, that is going to meet the losses, especially iron losses. Okay, these two factors we need to remember under no load conditions. So whatever the power you are drawing, most of the power is going to be used for the meet the iron losses. Okay, so we know that efficiency is nothing but, we can write it as output power by input power. And one more way you can write it as input power, also you can write it as output by losses. Okay, if losses are more, then efficiency is going to be reduced. Okay, the main reason is high fixed losses. That means fixed or constant losses in comparison to the output. Okay, our suitable option is C. Okay, if at light load or no load conditions, whatever the power drawn, most of the power drawn is going to be utilized to meet the constant losses. So that's why efficiency is low at light load condition or no load conditions. Let's move on to the next question. The next question is about a 2 kVA transformer has iron loss of 150 watts and full load copper loss of 250 watts. The maximum efficiency of the transformer would occur when the total loss is. This is very, very important. Okay, very, very important question. Many times it is repeated. Okay, many times it is repeated. Most of the students are going to do mistake. Most of the students are going to do mistake while solving this question. Okay, so we need to understand the basic concept of maximum efficiency. When you are going to get maximum efficiency, okay, constant losses, our constant losses will be fixed. Constant losses are going to be fixed. Constant losses going to be equal to the variable losses. Okay, variable losses. That means these variable losses are going to be vary. Constant losses are going to be fixed ones. So we need to make the variable losses equal to the constant losses. Okay, then only you are going to get the maximum efficiency. At maximum efficiency, what is going to happen? Constant losses going to equal to the variable losses. You can write like this. The variable losses we need to make it as constant losses. That means what are the variable losses? Copper losses. Okay, so the total loss of the transformer you can write it as iron losses plus copper losses. Iron losses already given 150 watts. Okay, what we have to calculate the copper loss. How we are going to calculate the copper losses? We need to reduce the given copper loss at full load is 250 watts. But if you run our transformer at full load, we may not get the maximum efficiency. In order to get the maximum efficiency, these copper losses need to be dropped down to reduce to 150 watts. Then only our efficiency is going to be maximum. So our copper losses are going to reduce to 150 watts. Then total losses is going to be 300 watts. Okay, the total losses is going to be 300 watts. Is it clear? Okay, so the question is very easy. We all know that at maximum efficiency, constant losses is equal to variable losses, but the given data is getting little confused. Okay, in copper losses they given 250 watts, iron losses they given 150 watts. The total losses you can get it as 400 watts, but that is not correct. Okay, so we need to read the question very carefully. At maximum efficiency, we need to bring down the variable losses to the constant losses. Then only we are going to get the maximum efficiency. Is it clear? Okay, we are going to wind up the today's session with this question. Okay, if you have any doubts, please chat over the comment box, and if you want any support regarding your preparation, we can contact our contact number as displayed in the screen. We are providing test series, we are providing offline classes, we are providing personal guidance to the preparation also. Okay, any help you want, you can freely contact to the number. Our team will support you. Okay, thank you students. We'll meet tomorrow 6 o'clock, the same time.